All right, so let's do some more practice with these types of Lewis structure VSEPR problems. So this is an interesting one. We have 4 atoms, HONO, HONO. And so first we're going to have to figure out what is the central atom, right? To try to line this molecule up properly, get our skeletal structure. We could also come up with the valence electrons first, but we'll do that in a second. Okay, so remember the least electronegative atom is going to be your central atom in the absence of any other information. We're not given any other information here. That excludes hydrogen. Hydrogen can never be at the center because hydrogen can only bond one thing. So nitrogen is going to be our central atom here. Oxygen is to the right of the periodic table, is to the right of nitrogen on the periodic table. So if you remember your periodic trends, that tells you that nitrogen is going to be less electronegative than oxygen. And so that's going to be at the center. So our skeletal structure is going to look like something like this, right? We know hydrogen has to be on an end somewhere, and nitrogen is going to have to be in the center of these two oxygens based upon our logic. And that's, you know, usually, for the sake of the exam, I'll always write out, if there's a complicated one like this, I'll write out the molecule, kind of giving you a guide as to what the structure actually is. And so you can see I wrote it as HONO because that's actually what the skeletal structure is. So anyway, let's do valence electrons. So valence electrons, we have 1 for the hydrogen, 1 for the first 6 for the first oxygen. It's a chalcogen, 2 away from the noble gases. 5 for the nitrogen, and another 6 for the other oxygen. That brings us to, what, 18 valence electrons. Okay, so let's connect these atoms by single bonds to start out. And now let's just try satisfying the octet rule. So we've put down 2, 4, 6 valence electrons. That means we have 12 valence electrons left. So if we try to satisfy the octet rule here, we're at 2, 4, 6, 8, 10, 12, 14, 16, 18. And so we've run out of electrons at this point. And so what do we have to do? Well, we're going to have to make a double bond because we don't have the octet rule satisfied, right? 2, 4, 6 for this oxygen. 2, 4, 6, 8 for this nitrogen. 2, 4, 6, 8 for this oxygen is good. This oxygen is not good. And so to satisfy the octet rule here, we're going to want to bring down a lone pair from the nitrogen and convert that into a double bond. And so now let's take a look at all this. We have 2, 4, 6, 8 for the oxygen. We have 2, 4, 6, 8 still for the nitrogen, and this other oxygen we didn't change. Hydrogen we have duet rule. So we're good. Total number of valence electrons we can check: 2, 4, 6, 8, 10, 12, 14, 16, 18. So that is the Lewis structure. Now it's asking about the steric geometry. And well, it kind of depends. There's multiple bonds here, which one we're talking about. But let's start off with the central atom, what we're calling the central atom, nitrogen. And so our steric geometry is how many bonding sites plus lone pairs, number of lone pairs, right? So we have 1, 2 bonding sites. Remember, a double bond just counts in this counting scheme as 1, okay? So it's number of bonding sites, not number of bonds. So it's 1, 2, and then we have a third bonding site or lone pair here. So 1, 2, 3. So steric number is 3. That means our steric geometry is trigonal, planar. It's just a planar triangle. Okay, if you put 3 things as far apart as you can in 3-dimensional space, they actually go in 2-dimensional space in a triangle. That's just the farthest part they can be. And so our idealized bond angle there, well, is 120 degrees, right, for equilateral triangle. But we have a lone pair, and so that lone pair is going to take more space, so it's going to be less than 120 degrees. So in our shape, what would our molecular geometry be there? Since we have one lone pair, our molecular geometry is just a triangle with one of the vertices removed. That gives you a bent shape. Okay, so really drawing this as a line like that isn't an accurate representation, but we didn't know that when we started out. Okay, what about this oxygen? This oxygen is steric number is 4. Why is that? It has 2 bonding sites and has 2 lone pairs. Okay, so that gives you 4. That gives you a steric geometry of tetrahedral. And a molecular geometry, tetrahedral with 2 lone pairs. You started with the tetrahedron, has 4 points. You've removed 2 of those vertices, and so that gets you also to bend. It's getting to bend a different way. It's getting to bend from a tetrahedron, but there's 2 ways to get to bend. Okay. And so again, now we can think about, okay, what would the geometry be here? That bond angle be here? It's going to be different, right? It's idealized bond angle for tetrahedron is 109.5, but again, we have lone pairs there, so it's going to be less than 109.5. All right. There's also one extra thing we can do on this type of problem. We can ask about hybridization, just reviewing all sorts of concepts here. And so remember, that was just based on the steric geometry. So if you have a steric geometry of 4, you're going to need a hybrid orbital of 3 orbitals. That's the sp3, caused by mixing 1 s and 3 p's. So that would be the hybridization of the oxygen. The nitrogen there has a steric geometry of 3, so that would be sp2, right? 2 p orbitals and 1 s mixing together. That's going to be steric number 3. And then we can also do this terminal oxygen at the end. 1, 2, 3. It's going to have a steric geometry 3, 1 binding site, 2 lone pairs, and so that would also be sp2. Okay, so a little more complicated problem there, but nothing that, I don't expect you to not know, so you should know it.